In this video, we're going to learn how to model and solve free damped motion in a mass spring system. We'll start by deriving the differential equation that models the motion and then solve it to see how the behavior of the solution depends on the damping constant. We'll then work through an example of overdamped, critically damped, and underdamped motion. Let's get started. Let's begin by deriving the differential equation for a mass spring system with damping and no external forcing. In these diagrams, we have a mass M that's attached to a spring and a dashpot. When the spring is not stretched or compressed, the mass is located at x is equal to 0, and that's called the equilibrium position. When the spring is stretched, x is greater than 0, and then when the spring is compressed, x is less than 0. The forces that are acting on the mass are the force due to the spring, and that's equal to minus kx, where k is the spring constant, and then the force due to the dashpot, which is minus c times dx dt, the velocity, where c is the damping constant. Newton's second law of motion states that the net force acting on an object equals its mass times its acceleration. In a mass spring system with free damped motion, the net force acting on the mass is the force due to the spring plus the force due to the dashpot, and all of that is equal to mass times acceleration, where the acceleration is just the second derivative of the position. The equation that describes the motion of the mass is just m times the acceleration plus c times the velocity plus k times x, and that's equal to 0. This equation is called the equation for free damped motion. Let's now talk about how to solve this equation. We're going to start by dividing all the terms in this equation by m, and then we're going to let c over m equal 2 lambda, where lambda is greater than 0. This is just for algebraic convenience. And then we're going to let k over m equal omega squared, where omega is the angular frequency. This equation is a second-order constant coefficient differential equation, and the solution of this equation takes the form x is equal to e to the rt. When we substitute this x up into the equation and simplify all the algebra, we end up with the characteristic equation r squared plus 2 lambda plus omega squared is equal to 0. We can use the quadratic formula to solve this, and we get a solution for r. And when we simplify this, we find that r is equal to minus lambda plus or minus the square root of lambda squared minus omega squared. Depending on the value of lambda squared minus omega squared, we can get 3 different types of solutions, and we're going to go over these 3 types. The first type of solution is when we get 2 distinct real roots, and this happens when lambda squared minus omega squared is greater than 0. In this case, our solution, x of t, looks like this, and it has no oscillation, and it returns to equilibrium slowly. This type of solution is called overdamped. The second type of solution that we can get is when we have 1 repeated real root, and that happens when lambda squared minus omega squared is equal to 0. The solution, x of t, looks like this, and it also has no oscillation, but because of these terms right here, it returns to equilibrium as fast as possible. This type of solution is called critically damped. The third case is when we get 2 complex roots, and that happens when lambda squared minus omega squared is less than 0. Here's what x looks like. Notice that there is a cosine and a sine in the solution, and because of that, this solution has oscillation, But because of this term right here, the amplitude decreases over time. This solution is called underdamped. Let's now look at this graph. I've included this so that we can visualize what these solutions look like. The overdamped solution in red has no oscillation and returns to equilibrium slowly. The critically damped solution in purple also has no oscillation, but returns to equilibrium faster than the overdamped solution. And then the solution in blue, that's the underdamped one, has oscillation, but its amplitude decreases over time. Let's now walk through an example of a mass spring system with damping. Suppose we have a 32-pound weight that's shown down here in our diagram, and it's attached to a spring with spring constant K is equal to 4 pounds per foot. It also has a dash pot attached to it, and that dash pot provides a damping force that is proportional to the velocity. The weight is released from rest at a point 1 foot to the right of the equilibrium position. That's going to be our initial conditions. We're going to let x of t represent the displacement from equilibrium measured in feet. We're asked to find the equation of motion and then classify the motion for each damping constant. And down here you can see that we have 3 different damping constants. Let's begin by writing down the equation of motion for a mass spring system with damping. That equation looks like this. We have m times the acceleration, which is d squared x dt squared, plus c times dx dt. That's due to the dash pot, plus k times x. That is due to the spring, and that's equal to 0. Now let's put in our initial conditions. The weight starts out 1 foot to the right of equilibrium. So we're going to say that x of 0 is equal to 1, and then the weight is released from rest. So that means it doesn't have an initial velocity. So we're going to say that dx dt at time 0 is equal to 0. We are given what c is. It has 3 different values. And we're given what k is, but we don't know what m is. So that's where we're going to start. Let's find m. To find m, we're going to use the formula that weight is equal to mass times gravity. So that tells us that m is equal to w over g. Our weight is 32 pounds. And because we're working with pounds, we need to let g be 32 feet per second, and we get a value of 1 pound second per foot. Let's make a note that k is equal to 4 pounds per foot. Now let's put these 2 values back up into our equation. So this equation is going to look like this. It is m, which is just 1. So we just have d squared x dt squared plus c. I'm going to leave it at c, and then for each of the 3 cases, we will put what c is equal to. So we have c times dx dt plus k, which is 4, times x is equal to 0. Let's go ahead and let's highlight this. And then I'm going to go up here and also highlight our initial conditions. So that's the system that we're going to be solving. Let's start with part A. For part A, C is going to be 6 pounds times second divided by feet. Let's go ahead and put that into our differential equation. This gives us d squared x dt squared plus 6 dx dt plus 4x is equal to 0. And then I'm also going to go ahead and put our initial conditions here. X of 0 is 1, and dx dt at 0 is 0. Since this is a constant coefficient second-order differential equation, we can let x take the form of e to the RT. When we plug that in and rearrange the algebra, we end up with the characteristic equation r squared plus 6r plus 4 is equal to 0. We can't factor that easily, so we are going to have to use the quadratic formula. And this gives us r is equal to negative b, so that's minus 6, plus or minus the square root of b squared, which is 36, minus 4 times a, which is 1, and then c is 4. And we're going to divide all of this divided by 2a, which is just 2. This gives us minus 6 plus or minus the square root of 20, all divided by 2. We can pull a 4 out of the square root. It's going to cancel with the 2 in the denominator, and this leaves us with a minus 3 plus or minus root 5. Our solution is then x is equal to c1 times e to the minus 3 plus root 5 times t plus c2 times e to the minus 3 minus root 5 times t. Let's go ahead and let's highlight this. There's our solution. Now what we need to do is find c1 and c2. We're going to use our initial conditions to get that. We have that x of 0 is equal to 1. X of 0 is going to just be c1 plus c2 because e to the 0 is equal to 1. And this is 1. That is one equation. And now to get the second equation, we're going to have to take the derivative. We have dx dt is equal to c1 times minus 3 plus root 5 e to the minus 3 plus root 5 times t plus c2 times minus 3 minus root 5 e to the minus 3 minus root 5 times t. Now let's let t be equal to 0. The exponents are going to go away, and we're just left with c1 times minus 3 plus root 5 plus c2 times minus 3 minus root 5. And that's equal to 0. And there's our second equation. To solve this, I am going to go up to our first equation and let c2 be equal to 1 minus c1. And I am going to substitute that in right down here. Let's go ahead and let's take this with us to the next page. And we can solve for c1. We have minus 3c1 plus root 5c1 minus 3 minus root 5 plus 3c1 plus root 5c1, and that's equal to 0. These two terms are going to cancel. We can combine the root 5s, so we get that 2 root 5 c1 is equal to 3 plus root 5. So c1 is 3 plus root 5, all divided by 2 root 5. It's very common that these constants just don't turn out looking very nice. Now we can find c2. Let's go back over here to the left. c2 is 1 minus c1. So we have 1 minus all of this, 3 plus root 5, all divided by 2 root 5. And this gives us 2 root 5 minus root 5, which is root 5. And then we have minus 3, all divided by 2 root 5. Now we can write down our solution and put our constants in. X of t is going to be e to the minus 3t, and then we'll plug in our constants. We have c1, which is 3 plus root 5, all divided by 2 root 5, and we're going to multiply this by e to the root 5t, and then we have our c2, which is root 5 minus 3, all divided by 2 root 5, and this gets multiplied by e to the minus root 5t. And there's our solution. I graphed this solution right down here. Our solution is called overdamped because the mass does not oscillate, and due to the damping, it returns to equilibrium slowly. Let's now go to case B. In case B, we are told that C is 4 pounds times seconds divided by feet. Our equation of motion is then d squared x dt squared plus c, which is now 4, times dx dt, plus k, which we were told was 4, times x is equal to 0. And then we have the same initial conditions. X at 0 is equal to 1, and then dx dt at time 0 is equal to 0. Just like we did for case A, we're going to let x be equal to e to the RT. When we plug that in and do all the algebra, we get the characteristic equation r squared plus 4r plus 4 is equal to 0. We can actually factor this. This is r plus 2 times r plus 2. That's equal to 0. And this tells us that r is equal to minus 2 and minus 2. So we have a real repeated root. And our solution is x of t is equal to e to the RT. So this is minus 2t. And then because of our repeated root, the second part of our solution looks like this. It's C1 plus C2 times t. I have a video on that if you need to review how to get that type of solution. Now let's find our constants C1 and C2. We'll plug in that t is 0, so x of 0 is e to the 0, which is just 1. So we get C1, and then t is 0, so we just get C1, and that is equal to 1. So that works out nice. Now we need to take the derivative, dx dt, and then we'll let t equal 0 after we take the derivative. We're going to use the product rule. Actually, before we do that, let's go ahead and let's plug C1 back up into here, and I think that'll make it easier. There we go. Now we're going to take the derivative of that. Using the product rule, it's the first, so that's e to the minus 2t, times the derivative of the second, which is c2, plus the second, 1 plus c2t, times the derivative of the first, which is minus 2e to the minus 2t. Now we can plug in that t is equal to 0. E to the 0 is 1, so this is just c2. T is 0, so we pick up a 1 times a minus 2. So this tells us that C2 is equal to 2. Now let's take this equation right here, and we'll come down here and write our solution. Our solution is x of t is equal to e to the minus 2t. C1 is 1, so that's 1. And then C2 is 2, so we have 1 plus 2t. And there's our solution. This solution is called critically damped because the mass does not oscillate, just like in part A, but in this case, the mass returns to equilibrium more quickly than in the overdamped case. Now let's do case C. For case C, we are told that our damping constant C is 2 pounds second per foot. Our equation of motion is d squared x dt squared plus 2 dx dt plus 4x is equal to 0. And we have our same initial conditions. X of 0 is equal to 1. And then dx dt at time 0 is 0. We let x be equal to e to the RT, plug that in, and then we get the characteristic equation r squared plus 2r plus 4 is equal to 0. We can't easily factor this equation, so we're going to use the quadratic formula, and we get that r is equal to minus b, so that's minus 2, plus or minus the square root of b squared, so that's 4, minus 4 times a, which is 1, and then 4. And we divide this by 2a, which is 2. This is equal to minus 2 plus or minus the square root of 4 minus 16, so that gives us a minus 12. Divide that by 2, so this is minus 1 plus or minus. We can bring out the square root of 4, which is 2. That cancels with the 2 in the denominator. So we end up with just square root of 3 times I because of the negative. When we have complex roots, our solution looks like this. It's x of t is equal to e to the minus t. That comes from that part of the term right there. And then we're going to multiply this by c1 cosine root 3t. That comes from that piece right there, plus c2 sine root 3t. Let's go ahead and let's highlight this. And now we can find c1 and c2. We know that x at 0 is going to be e to the 0, which is 1. And then cosine of 0 is 1. Sine of 0 is 0. That is equal to 1. So this tells us that c1 is equal to 1. Now let's find c2. To do that, we are going to have to take the derivative because that's our second initial condition. We'll use the product rule. So we have the first times the derivative of the second. Let's throw in here that c1 is 1. So this gives us minus root 3 sine root 3t. And then we have c2 times root 3 times cosine root 3t. Plus the second, which is cosine root 3t, plus c2 sine root 3t, times minus e to the minus t. I think if you're going to make a mistake, the biggest place to make a mistake here is to forget the second term. Now let's go ahead and let's let t be equal to 0. E to the 0 is 1, sine of 0 is 0. So we end up with just 1 times 0. Cosine of 0 is 1. So we pick up a root 3 times c2. And then from the second term, e to the 0 is 1, but there's a negative there, so we pick up a negative 1 times cosine of 0 is 1, sine of 0 is 0. And this is equal to 0. So let's see. This gives us root 3 c2 minus 1 is equal to 0. So c2 is equal to 1 divided by root 3. That wasn't too bad. Now we can go ahead and rewrite our solution and plug in these constants. X of t is e to the minus t, and c1 is 1, so we just have cosine root 3t. And then let's see, c2 is 1 over root 3, so we add 1 over root 3, and that multiplies sine of root 3 times t. And we did it. There's our solution. This type of motion is called underdamped because the mass oscillates. That's due to the sine and the cosine term. But notice that the amplitude decreases, and that's due to our decaying exponential term. And that's it. You now know how to model and solve free damped mass spring systems and then classify the motion based on the damping constant. You should now be ready to work through a practice problem on your own. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.